Ladies and gentlemen, let me introduce Ivan Sechin. With his illuminant talk about Ruijsenaars duality for BCD Toda chains. And he's the most important organizer of the conference.
My talk actually will be shorter than the introduction. Yeah. And I will explain you Ruijsenaars duality for BCD Toda chains. And it is a phenomenon when on the same phase space we have two classical integrable systems, and coordinates of one system are action variables of the other and vice versa. So I will deal with Toda chains related to root systems B, C, and D. So just ordinary open Toda chain relates to A-type Lie algebras. And the nearest neighbors interaction is actually connected with A-type root systems. And it can be easily generalized. And all these systems are classically integrable. It means that we have, on our two n-dimensional phase space, we have n-independent Poisson-commuting integrals of motion for these systems. These systems are really nice. We can solve it. We can solve the equations of motion in quadratures. And they are quite universal. So integrable systems appear everywhere. And Ruijsenaars duality is a phenomenon when we have Hamiltonian of one system. On the same time, we can construct very trivial integrable system. We can just take coordinates. And they also trivially commute on this phase space. And the duality shows that we have Hamiltonians of one system and coordinates of the other one. And Hamiltonians of the other system is coordinates of the original one. And the most known example of this duality is duality between Cauchy systems and Ruijsenaars systems. So now you can see this square called Etep square, where different systems of Cauchy-Ruijsenaars type are written. And rational trigonometric and elliptic dependence on coordinates are switched with the rational trigonometric or elliptic dependence on momenta. So, for example, rational Cauchy, which is a system with a rational dependence on momenta, is dual to itself. But trigonometric Cauchy, which is rational on momenta and trigonometric on coordinates, dual to rational Ruijsenaars system, which is trigonometric in momenta and rational in coordinates. Yeah. And in my talk, I will show you how to construct Ruijsenaars dual to Toda systems. And this integrable system is called Goldfish model. It has trigonometric dependence on momenta and rational dependence on coordinates, just opposite to the Toda case, as I explained before. And this system can be considered as a strong coupling limit of a rational Ruijsenaars system. While open Toda chain also can be considered as an inexemtive limit of the trigonometric Cauchy system. And we have Cauchy and Ruijsenaars dual to this duality, and those systems are also dual after these limits. Yeah. So, and it was the introduction. Let's go to the technical part. The method how we do it is related to the Hamiltonian reduction. So it is also the very nice source of classical integrable systems. So let us have a large symplectic manifold, but with large symmetry group acting on it. And let us have Hamiltonian action of this Lie group with some equivariant moment map. In this case, we can reduce our phase space, and we have a very large phase space with a large dimension, and we can reduce it. First, we can consider the pre-image of the momentum of some value, and then factor it by stabilizer for some fixed value, lambda. And it was large phase space, and it is a smaller phase space. And the theorem of Hamiltonian reduction says that under some conditions on this Hamiltonian action, this reduced phase space is also a symplectic space. And we have a symplectic form here, which can be naturally computed from this relation. So we have a projection of our prey image to reduced phase space, and we have an immersion to our original phase space. And also, if we have some invariant, G-invariant functions on the large phase space, under this procedure, on the same diagram, we can define a function after the reduction. That's why this method provides us a source of integrable systems. We can consider some simple functions on a large phase space, probably few of them. And under this procedure, get non-trivial functions on the reduced phase space. And if the number of independent functions is enough, we have an integrable system on the reduced phase space. Yeah. So let us have just a complex Lie group G, and let's consider its subgroups. Unipotent ones, which is in A case just upper and under triagonal matrices with ones on diagonal. And for example, in type C, it is better to choose this Q-symmetric form to be matrix with ones and minus ones on the alternative diagonal. And in type C, this unipotent group is also a subgroup of these matrices with ones on diagonal and upper triangle. And let us also have maximal compact subgroup K, which is just a unitary group in type A, and some subgroup of unitary group in types B, C, and D. And in all these types, actually, we have N plus and K, either under upper triangular with ones on the diagonal, or subgroup of unitary group, which is useful in the construction. Okay, and our large phase space before reduction will be cotangent bundle to a Lie group. It always can be trivialized, for example, by left translation. And as any cotangent bundle, it has a canonical symplectic structure on it, written here. And we have here G is a point on the base, and X is a vector on the fiber. And under this canonical symplectic structure, our axis has just Lie algebraic Poisson brackets. And all elements of G, all group elements, I actually just commute in this symplectic structure. And we have a left and right action of group on itself, and its action can be lifted in a Hamiltonian way to the cotangent bundle. And we have left and right Hamiltonian actions. And to get this Toda or Goldfish systems, we need to have group N plus action from the left and group K action from the right. And those subgroups actions are also Hamiltonian. Yeah. So what is the reduced phase space here? We have our two moment maps, and we need to fix some values. And for K, let us fix just 0. And for N plus, let us fix just sum over simple roots of E alpha. Yeah. This choice of momenta has the maximal possible stabilizer here. And so we reduce in a maximal way. So the dimension of this reduced phase space is minimal possible of non-trivial ones. And on this phase space, on the larger one, on a cotangent bundle, we have two families of invariant commuting functions. First, we have traces of X. And the Poisson brackets on X are just Lie algebraic brackets. So traces of them are commute. And under this action, and plus times K, X transforms just by a joint action of K. So it is invariant. And we also have minors of the matrix G cross. So G, all elements of G commute, so they are also commute. But they are also invariants, because our K's are unitary matrices. And N has ones on the diagonal. And N cross is lower triangle with also ones on the diagonal. So all lowest right minors are actually invariants of this N plus times K action. And on this larger phase space, the number of these Hamiltonians is not enough to have an integrable system. But when we reduce, we have invariant functions, and after reduction, they also give some functions on the smaller phase space. And they are also commute in the smaller phase space. And the number of independent ones is rank G, which is twice smaller than the dimension of the symplectic manifold. So we have a classical integrable system. Yeah. And Toda system can be obtained in the gauge. So we have the action of this stabilizer. So let us use this stabilizer action to make G diagonal by Iwasawa decomposition. And after that, resolving this momentum map equation, we can have Toda chain Lux operator and its Hamiltonians. And in this gauge, X is non-trivial, but G is trivial. G is just matrix diagonal with coordinates on the diagonal. So with this GL are just coordinates, but these X, IL, are Toda chain Hamiltonians. And the opposite case, how could we construct a dual system? Let's consider so-called Moser gauge. The opposite case. Let us use this adjoint action of K to diagonalize X. And denote these elements of X as dual coordinates. And the remaining gauge freedom can make matrix G lower triangular. And also, we can rewrite the momentum map equations, and we will solve them a little bit later. But let us know that XL, the traces of XL, are some symmetric functions on coordinates, and GL are dual Hamiltonians, so Hamiltonians of a dual system. So we have this situation of Ruijsenaars duality. We have coordinates of one system action as action variables of the other one, and vice versa. The same, yeah, and the gauge. No. This one is the same. Yeah. The same.
The same.
Yeah, the equation of momenta are the same, but we use our gauge freedom to solve them.
Okay.
Yeah, so here we use the gauge freedom to make G lower triangular Borel matrix, yeah, and we can decompose it, so we can rewrite the momentum map equation in this way. Yeah, and how to solve these momentum map equations here? So we have, let's start from the type A. We have diagonal matrix X, and we have this momentum map equation, and it is just a recursive formula for elements of G. So we have some non-fixed diagonal elements, that's denoted as A hat. And all the elements below the diagonal in this gauge can be obtained recursively from the momentum map equations. Yeah, and actually the same happens in type C, we have, because we chose our skew symmetric form to be ones and minus ones on the on the alternative diagonal, we will have this diagonal matrix of this form here. And after fixing the diagonal elements of G here in one block, we can also recursively reconstruct this matrix G from the momentum map equation. And Hamiltonians of Goldfish system are minors of G cross. So, and all these matrices are actually very nice to compute these Hamiltonians explicitly using Cauchy-Binet formula. But I will skip all these computations and I will skip all these details. Yeah, and Hamiltonian have this form. Yeah, someone can recognize some classical version of McDonald operators, something like that. Yeah, and we can make this. We can make a change of variables to make them more symmetric. And in type C, actually, we have a more complicated matrix than in type A. But to compute this L times L lower right minors, we need to use only this lowest block. And it can be rewritten as a folding of some GL2n case matrix. So we can just denote A coordinates as A hat minus 1 and minus Q. And this lower part of matrix in type C is the same as a lower part of Z matrix in type A, but for this choice of coordinates and momenta. In types B and D, it is a little bit more tricky, but still doable. Yeah, and as it was expected, in type C or in types B and D, we have this Qi plus Qj in the denominator. Yeah, so, and now let's see the overview of these systems in types A, B, C, D. So we have some difference here. Yeah, those are A, B, C, D Toda chains. Yeah.
So can you mention, so how do you construct T? This is really exactly type A plus Cauchy-Binet, or you need to do something in addition?
We can make the calculation knowing the type A. In type C, this matrix, we need to compute the minors of this matrix times its transposed. Yeah.
Yeah, and because it looks like A, but you say you choose a different set of coordinates.
This part, this A, this top part, doesn't look like A-type matrix. Yeah. But this one looks like type A matrix, but with two n coordinates and two n momenta. And first n are just ordinary coordinates, and the other ones are just minus coordinates. Yeah, and you can see it also on the formula of Hamiltonians. Yeah, so type C is just folding of type A. We have type A difference of coordinates, and let us have here coordinates Qj and coordinates minus Qj, and we explicitly have all the differences here. Yeah, and this 2Qi is Qi minus Qi. Yeah. And types B and D are a little bit more tricky, but still doable in the same way. Yeah. So that is the overview of these results for BCD dual system for Toda chains. They also can be obtained as some limits of corresponding Ruijsenaars systems. Yeah. But And it is nice that all Hamiltonians here can be computed explicitly using this Cauchy Binet. Yeah, it is my message for today, and we have time for questions.
Any questions?
Do you know the analog of this goldfish for relativistic Toda?
We are doing this, but
So there are problems, or what?
it should be a trigonometric goldfish.
Yeah, well, it's known.
And we know the formula.
It's known for two particles, but I don't know generally how easy it's to take the limit of the self-dual Ruijsenaars system.
Yeah, unfortunately, we don't know the limits, but we are working on this. Yeah, it is the most interesting problem here. Yeah, to do it for relativistic case. So we know the answers. We know this trigonometric goldfish are nice even for more particles than 2. But we need to prove the duality in some way, doing some Poisson stuff or.
Did I understand correctly that the C case can be obtained from the A to N case by the folding? Is it
true?
Also for B and D?
Yes.
And is it true for all high Hamiltonians as well?
Yeah.
So there is kind of. So then, in this sense, the only independent system is A.
No. B and D is not from A. B and D can be obtained by folding B from D or D from B. I don't remember. B from D.
But D can be obtained by folding from A. No. Okay.
D case appears to be the most tricky one.
So only the C case can be obtained.
Yeah. C is the simplest one, so that's why I write formulas for C. C is the simplest one. It appears that C is the simplest.
Okay.
Vanya, there is a root system, so to say, a root system T, folding A to N plus 1, just folding, right? It is T. It is not a special name for this. Maybe your formulas will be simply more uniform for BC.
Yeah, probably.
Just examine T.
Other questions?
So you mentioned generalization to trigonometric case.
Yeah.
Or what is Vasilev in hyperbolics. Ruijsenaars is most interested in hyperbolic cases are dual.
Yeah.
So you mentioned that you are working on this problem. So what is the big phase space and what is the symmetry action for the trigonometric case?
Symmetry action is actually non-trivial. So the big phase space should be the Heisenberg double of Lie group. Yeah, but symmetric action is not really clear now for me. Yeah. So we are working on this, but still not easy.
Yeah, I have two technical questions. The first question is about the Moser gauge. You mentioned that we can always diagonalize the matrix X. Why it's possible?
We have a momentum map condition that projection on the subalgebra K is 0. So for type A, we have a matrix whose anti-Hermitian part is 0, so it is Hermitian matrix. And we can diagonalize it by unitary group action.
Okay.
And yeah, the same for BCD.
And I guess on the slide 10, could you please remind what is the matrix P?
Matrix P is a matrix of ones on the alternative diagonal.
Okay.
Yeah, so this skew-symmetric form is matrix 0P minus P0. It's a block matrix. And P is matrix of ones on the alternative diagonal.
Other volunteers?
There is a conceptual question, with operators, if you go to operators, connection is just Harish-Chandra or whatever transform, Fourier transform. Do you have, generally it is supposed to collapse in the quasi-classical limit, but I'm not quite sure. What do you know?
I'm not sure also.
But this is very interesting, you know. When you go to operators, things are much nicer. You have integration with spherical whatever function or Whittaker function. Whittaker in your business, Whittaker function, right?
Yeah.
Do you have
and
some
also
traces?
trigonometric case is nice in quantum
There
case.
must be some map.
But classical,
pretty much direct map, but
I don't know. It is interesting, but I don't know now.
One more question. So can you show the other slide again?
Which one?
14. So the most interesting thing about Toda is when n goes to infinity, when there are solitons in Toda, or there are some hyperelliptic solutions or whatever. Are there any? I mean, if you take the limit n to infinity, in some sense it doesn't matter. It's Z Toda. Are there any dualities like this for infinite Todas?
Well, unfortunately, I don't know. It is interesting, but I don't know.
And a related question, there are also Toda field theories. So Toda field theories have kind of these dual counterparts.
Unfortunately, we don't know also.
Okay. Thank you.
All of these are interesting questions. Yeah.
Other guys, we have a few minutes for other questions. Okay, so maybe I'm asking you, so why you don't work with exceptional algebras?
Because it's more difficult technically. So these BCD cases can be done quite universally, and for exceptional algebras, you need to have more technical work.
And when you have a fine case, you can also work with this, or it's fail absolutely?
A fine case, it's probably much more complicated because the dual system should have elliptic dependence on momenta, and it is very non-trivial. So it can be done for two particles, but for a larger number, these systems with elliptic dependence of momenta is terra incognita. You can see an expert here.
Supercase. Can you do something in supercase?
At least for OSP 1 to n, it should work, but probably it should work also for the other cases.
Okay, thanks. Let's thank you again.